Looks like a soap opera, right? Number 4. So let's recall what happened in the previous. Okay, so the setup is that we have VQ, a quadratic Q vector space of signature and 2, and I always assume from now on n bigger or equal to 1. And I will fix also L inside V a maximal quadratic lattice. And yesterday I convinced you that associated to this data we have first of all a complex manifold MLC. So by this I denote the Shimura variety that you get taking inside G spin of V the adelic point. It's adelic points, in fact. A compact open that has been defined also this morning and we saw yesterday. Then above that we had Kuga-Satake abelian scheme or abelian variety. And then we had other objects. We had a variation of structures inside the endomorphism of H1AZ. And to this we also associated a module with connection and filtration, satisfies Griffith's transversality, and so on and so on. Okay? Okay, so now I want to get to canonical models. It has models of all these objects over Q, and then two integral models. So I will not give many details, but at least discuss a few points, since this morning already Jan was referring to that. So first of all, we can descend to Q via the theory of canonical models. And we get ML, which is a variety over Q. And again, we have Kuga-Satake abelian variety. The module with connection and filtration we can also descend. Descending filtration. Here we have a variation of Z-odd structures that you can see as a Z local system. So you can view it as a representation of the usual topological fundamental group. If we talk about varieties, we don't have the usual topological fundamental group anymore. We have the algebraic fundamental group. So we expect to replace a representation with Z coefficients of the topological fundamental group with a representation with Z hat coefficients of the algebraic fundamental group. And in fact, for every prime P, we get a Lis et al. ZP sheaf plus bilinear form. Inside, well, what is, if you have an abelian scheme, what is the canonical way to associate to it a Lis p-adic et al. Sheaf? You take the p-adic Tate module. Okay? So inside this p-adic Tate module, relative of Kuga-Satake, we have, which is a representation of the fundamental algebraic fundamental group of ML, you have a sub-representation. Okay? And here the translation is that, I'll put it in between, from analytic to algebraic, that over MLC, my V et al. P is really simply the p-adic completion of my Z local system. Okay, so that object I'm claiming simply descends to the algebraic variety ML. Okay, great. And actually, since we have a bilinear form, we also have a dual with respect to this bilinear form, and the quotient will be L isomorphic to L dual modulo L tensor ZP. That's a finite group, so it's just taking the P part of this finite group. And exactly as L dual modulo L here, as I mentioned yesterday, it's a constant sheaf. This will be a trivial representation of the fundamental group of ML. So you have such exact sequence, and these you can embed inside the endomorphism TPA tensor Q. Okay, so with this data we can define now over Q models of the Heegner divisors that we saw yesterday and this morning over C. Now the correct, because yesterday it was the wrong one. If you do things analytically, you get wrong answers. So the correct definition of Heegner divisors. So you have, so you fix, as we saw yesterday, a positive rational number. You take a mu, which is a class in L dual modulo L, and then you define Zm mu over ML as the object representing the following. So Zm mu of a scheme S. So S scheme over Q. It's the set of pairs. It was briefly mentioned today. Well, it should be a morphism over ML. So the first piece of data is a morphism from S to ML as schemes. And then I have an F with the property that F is a special endomorphism. So I pull back the Kugas-Satake from ML to S. I get an abelian scheme over S. I can consider its endomorphism algebra. And I demand two things. The first condition should be very familiar to what we discussed already yesterday. So F composed F is just the isogeny of A given by multiplication by my rational number M. And the second thing, I demand that for every P, so I have my V et al. P dual inside the end of TPA tensor Q. If I have an endomorphism F, it will define an endomorphism of the p-adic Tate module by factoriality. So in here I have my et al. P-adic realization, so this small r to mean a realization of F. Other questions? Okay. And the second request is that there exists for any P an element VP in here mapping via L et al. P-adic is a specific et al. Realization, okay? Such that, so I'm writing now from right to left, the class of VP in L dual modulo L tensor ZP is equal to the class, the P part of the class of mu. So here I'm using this exact sequence to see my little v, the P part, in the P part of L dual modulo L, and I wanted it's the P part of my mu. Okay, so you see that we got rid completely of analytic definitions and we gave an intrinsic definition. It's different from what we saw yesterday, because yesterday we instead considered the image of these objects inside the complex valued points of ML. And there is a distinction. So this map is finite and ramified, but it could be finite to 1. So it could have some multiplicities. Okay? Still, you can talk about a Cartier divisor, because if you take a point in here, okay, then you can prove that the complete local ring coincides with a divisor in the complete local ring in ML. So it is, except for this phenomenon of being finite to 1, really a Cartier divisor, and we speak of a Heegner divisor. Okay, now, before we move to another blackboard, we see our strategy. If there exists an extension of ML over spec Z of ML over spec Q plus, in fact, for the definition of the Heegner divisors, we didn't really need the VDRAM. I will mention why I mentioned this VDRAM. We just needed this part of the blackboard plus something plus, well, Kugasatake and some realization of A okay, so I suppose I can extend ML to a scheme over Z. I can extend Kugasatake abelian scheme, okay? And then considering various realizations, I have a sub-realization that mimic the construction that we see over the complex numbers and over Q. Then you see that we can define in the same way as I did there, integral models of my Heegner divisors Z and mu. What is this question mark? Okay, so certainly, for example, if you are away from a prime L, you want to consider p-adic realizations in the tal sense, as I wrote there, for every p different from L. Okay, so that's a request that I demand. Then, working over spec Z, I have the extra complication that I also have points in characteristic P. And then working with the p-adic realization in characteristic P, it's not very good. For example, in the interesting situations, this Kugasatake will be supersingular. So the end TP of A in characteristic P will be 0, because the Tate module is, the P rank is 0, so it's not a very interesting condition. And the question mark in that case has to be replaced with Diogenes theory or crystalline theory. So I don't want to be more specific than that. I just want to say that you can extend A and extend V inside the endomorphism of the realization etar or crystalline of A. Then you can mimic the same definition that I gave to the right-hand side and get integral models. And if you can sort of study the deformation theory, you can still prove that they are Cartier divisors and so on and so on. Okay? So I'm simply outlining the strategy and not mention anymore when this really applies and how one does the computation actually of the deformation theory. Okay.
And the integral model are really over spec Z. You don't need the base change to
over spec. I want over spec Z. Yes. Okay, so integral models. So now I have to convince you that when does ML plus A plus V question mark exists. Okay. And the first step is over certainly by work of Keysing and Vasu. And do actually. So they exist over Z, where I invert 2 and the order of the discriminant group of my lattice. And in fact, in that case, is even smooth over the spec of it. And what is the strategy? The strategy is the following. So you have Kugasatake. Yesterday I waved my hands saying that there is a polarization, and indeed there is a polarization. So the Kugasatake abelian scheme plus the polarization gives you a map from ML over Q to some Ziegler modular variety of a huge dimension, because it will have as a homology C of V, so it's 2 to the power n plus 2. But even if it's a high dimensional Ziegler modular variety, that we are relieved because it has a nice structure over Z. And you use this structure over Z simply to define this integral model as the normalization of that Roman font ML over Q inside the Ziegler modular variety over spec Z. Okay? As such, it's not very useful because, for example, how do you deduce this and how do you get this and this? But Keysing's theory and the use of Keysing modules allows you to control the complete local rings of this normalization. So you take a point in the special fiber. You can work over, say, completions of Z at primes. You can lift those points to characteristic 0. Okay? Then you prove, using Keysing theory, that over this one-dimensional DVR direction, these data extend. And then you check that if you look in the locus inside the Ziegler modular variety, where all this data extends not only along this DVR, but you look the maximal locus where it extends. This is on the one is given by a local model, typically a quadric, exactly as the symmetric space, which is smooth. Okay, and then that must be the normalization completed at that close point. That's the general strategy. Okay. Then Madapusi Pera plus epsilon of our first paper. If at primes that strictly divides the order of L dual modulo L. In that case, the variety, the model that you get, so you can take away those primes for here. At that point, the model that you get is not smooth anymore, but still you have a control. It's regular. Okay. Madapusi Pera also at 2, if L is, if 2 does not divide L dual modulo L. In fact, you should say Madapusi Pera plus Ban-Tsukim. And then, if you look at the thesis of Madapusi Pera, which has appeared by now, he has also a definition. So the only remaining case, since we assume that our lattice L is maximal, except for if P odd and P squared divides L dual modulo L, okay, this is the only case left for P odd. So the maximality of L assures that either P does not divide L dual modulo L, or P strictly divides, or P square divides. No other possibilities. Madapusi Pera defines a model defines ML or spec Z localized at P, plus also Kugasatake, but not our realizations that we want, for example, the crystalline realizations. And also another very bad point, other problem, there are points missing in his model in characteristic P, in the sense that you have points in characteristic 0 over Q, for example, our CM points, that you want to see how they extend. You close them up inside your model. You know that the associated Kugasatake extends over this thing by Néron properties. So you're not in a phenomenon where in characteristic P, your point goes to the boundary. So you expect to meet somewhere your model, and it does not. So there are really missing points. So what we do, so it's the second paper, the one that I cited at the beginning of my lecture. For those primes, we embed L as a quadratic form inside a bigger quadratic lattice of signature and tilde 2, such that L tilde is self-dual at the given prime P, which is bad for L. So P is bad for L, but it's good for L tilde. And then we define ML at least over ZP as the normalization of ML. So this maps to some ML tilde because you have a map compatible with quadratic forms. This has a very nice model ML tilde over ZP, which is even smooth. And you simply, this map is finite. You simply normalize this model over ZP inside this generic fiber. And let me write the proposition that you get in this way. So at least we have a model which apparently strongly depends on the choice of a self-dual lattice containing L. And the proposition ML over ZP does not depend on the choice of L tilde and Q tilde, and then all these models glue to give ML over spec Z. That's the first property. Moreover, one, Kugasatake extends. Moreover, we can extend. So we cannot extend V with its realizations, but we can extend field 1, which is was our omega, field 1 of V de Rham, which is a line bundle over ML. How you define it? So you have the embedding. Here you have a V de Rham tilde over it, and here you have a field 1. So this is an omega tilde, and we just pull back this omega tilde to the normalization. And again, this does not depend on the choice of the self-dual lattice in which we embed L. Okay, so now we have a metroized line bundle over this arithmetic scheme ML. And finally, even if we cannot extend this strategy because we cannot extend those objects for prime such that p squared divides the discriminant group, still we can apply this strategy to define the Heegner divisor. Well, what do you do to extend it, to define it? We need to specify when when an endomorphism of Kuga-Satake is special. Okay? Well, we can again resort on these auxiliary, much bigger Shimura varieties, and we say, look, I take a special endomorphism of my Kuga-Satake. So there is a relation between Kuga-Satake on ML and Kuga-Satake on ML tilde. So in particular, an endomorphism of Kuga-Satake at this level induces on the image an endomorphism of the Kuga-Satake on the bigger Shimura variety. And I say, well, I declare this endomorphism to be special if it is special at this level where this definition makes sense, because I can extend, thanks to the work of Kiesing and Vasu, P, I can extend this definition and the original naive strategy. And in fact, one can say something slightly more precise, because, as I said, original method for p squared dividing the discriminant group of Kirti was not too far from giving what we want. There are only essentially very low dimensional loci that you cannot control, where things can go very, very bad. So if you're interested in properties that you can check, for example, in codimension 2, still his proof can be used to deduce this, that his model that he has defined are open subsets of the model that we get here. And since he has a good control of his models, we deduce property of our ML. And then one can actually prove, just to say that this definition with the normalization gives you a way to control the special fiber as well, that for every p the fiber MLFP is geometrically connected as in the generic fiber, plus geometrically normal. So for example, you don't get regularity, which is bad for arithmetic intersection theory, but still it's good if you want to extend points from characteristic 0. So geometrically normal if 1, L is self-dual at P, 2, P squared does not divide the order of L dual over L, and 3, P is odd and the integer n is bigger or equal to 5, and this is due to the fact that, as I said, Kirti can control what happens in high codimension. So if you want, for example, to check normality by using Serre's criterion, it's enough to know what happens at codimension 1 points, essentially. And that's what is guaranteed by that requirement that n is bigger or equal to 5. OK, so I'm not going to use this theorem in any way. It's just to convince you, make some advertisement, that this bizarre-looking definition with taking normalizations still allows you to have some control on the end result. OK? OK. And in fact, I can also add another property that you can prove in the same way that, for example, my ZM mu's are flat. You prove it in the same way over Z 1 over 2 for n bigger or equal to 3, or, and also at 2 if 2 does not divide the discriminant group. And again, how do you prove it? Well, essentially, you have to check that you don't have vertical components lying fully in the Cartier divisor. But if you can control what happens inside your moduli in high enough codimension, you can check that the special fiber of ZMU does not contain vertical components. That's the rough idea. OK. Yes.
Okay.
Yes.
But the other things are more or less like by normalization.
So yeah, so ML is defined as a normalization, and then you use exactly that definition. Since Kuga's attack extends over ML, even if it's defined by normalization, for this definition, you just need the Kuga's attack. Plus, to check this property, you again rely on bigger dimensional, higher dimensional Shimura varieties in which you can embed things that are self-dual and where speaking about specialness makes sense. Okay? Yeah, so it doesn't matter what ML is, even if it's defined by the normalization. The important thing is that it carries Kuga's attack, and then it's a relative definition. So maybe it's not a good idea to change. No, OK. I obey the organizer. Just a look was enough. So where are we staying now? So far we defined, remember that at the beginning of, in lecture 1, I told you that I want to define an object ML with a metrized line bundle. Another object Y0 with an abelian scheme with CM by a ring of integers of the total reflex algebra, so that if you take the Hodge bundle with a usual metric, each will define, if you divide by the degree of Y0, the Falting's height, or of associated to the E sharp with the sharp CM type. And this is related. This is what we want to compute to get Colmez. And then I want to compare the Hodge bundle with its metric, pull back to YL, and my omega hat. Okay? And if you can say that these two line bundles over here, they're the same, comparing metrics and so on, except for finitely many bad primes, I have Colmez equality up to Q log of those primes. So far, we are here. Right? And now I have slightly less than an hour to complete the picture. So we move to big CM points. by the way, the first paper of the four of us that I mentioned has to do with the small CM points. So big CM points. So the starting point is our preferred CM field of degree 2D. And in fact, I will assume D bigger or equal to 2, because by the Charles-Albert formula for D equal 1, Colmez conjecture is already proven. And this will have a totally real subfield F. And in notation, I also want to label the number of embeddings. There are D, let's start with sigma 0 of F into the reals. And for any embedding of F, I have 2 conjugate complex embedding of E that I number C. Thanks. That I number in this way. And this sigma 0 is the fixed embedding that I have viewing E as a number field, so it's a subfield of C that enter in the definition of phi sharp, actually. And now I want to cook up from E and some extra data, a V and a Q. And the extra data that I need is the following, is the choice of a lambda in F such that sigma 0 lambda is positive, is negative definite, and sigma I lambda is positive definite for every I from 1 to D minus 1. Okay? With that, if I denote by W my E, so E will have many roles. It will be an F vector space, a Q vector space, a field acting, and so on. So even if it's always the same E, I try to keep different notations because there is a different emphasis on the structure that I'm using. Anyway, at some point you will get confused. And I will get confused as well. So let's try to not get lost at the beginning. Okay? So I have a quadratic form which is simply defined by taking the norm of x down to f, and I multiply by lambda. And then I also have a quadratic form that I get from this one, tracing down the form over f. Okay? And now, thanks to my choice, my V and Q has dimension 2D and has signature N2 with N2D minus 2. Okay, so starting from my same field, I cooked up a vector space, and then I can associate to that this whole mess that I've discussed in the last 3 lectures. Okay, now remark that I can take the Clifford algebra of V over Q thanks to this quadratic form, but I can also take the Clifford algebra of W over F doing the same construction. So this will be universal for F algebras with certain properties. And by the computation that we did for vector spaces of dimension 2, you get a quadratic imaginary extension of F. And, wonder, wonder, you get back your E. OK? So just a different way to realize E. OK. So now my big CM point, so CM points are just 0-dimensional Shimura varieties, or equivalently, they are Shimura varieties associated to the reductive groups, which are tori, which are alien. Okay? So I want to produce for you a torus associated to this data. And I do the following. And first, let me make a remark. So if K is a field over which, subfield of C, over which all sigma I are defined, and if I take the tensor product over F, do I want this? Yes? Okay, maybe let me immediately write. So I can, for every sigma I, let W sigma I simply be the base change of W viewed as an F vector space via sigma I over K. For example, here you could take, of course, K equal R. It doesn't matter, right? And then you see that the even Clifford algebra of V sigma I, it's simply given thanks to this property. It's simply the base change via F to K via the embedding sigma I into K, okay? But now I can embed this Clifford algebra, sort of, maybe I should write here. This Clifford algebra over, I can view this as mapping to the Clifford algebra over K of all my V sigma I, which is C plus of V tensor Q over K. And here I can take simply the product. This follows simply by the universal properties of my Clifford algebra. So for each of them, each homomorphism of algebras, where my F maps to K via the sigma I embedding, and then by universal property that admits a map. If I take the product over all D minus 1, on each factor, it's a ring homomorphism. On the product, it will not be a ring homomorphism anymore. It will be a multilinear map. So factors via the tensor product. And this I can write in another way. This is simply the value restrictions of GA from E to Q evaluated at K. So the fact that you have this factorization tells you that this is not a ring homomorphism, but at least it respects the multiplicative structure. So in this way, you get a map from the restriction E to Q of GM. The units in here to the units of C plus V. So this is defined over K. You can take K a Galois extension of Q and get this morphism by descent from Q to descent from K to Q. Okay, these I denote by TE. Inside here I have my G spin V. And the map, and the claim is that this map, in fact, factors via G spin V. Okay, so even if you are confused with this, let me describe formally what one has. So for example, we said if you take an element in F here, where does it map to? Well, we said on each component via sigma I, you embed your element F into K via sigma I, and then via this construction, you take the product, okay? So for example, you have TF that via this map goes to the scalars in here exactly via the norm map. And now here you can map it to TE modulo TF, and you get an exact sequence. Here we said that if you take the scalar, G spin modulo the scalar, you get SOV. And you get a map from TE modulo TF to SOV. Okay? So for example, let me describe for you, if you're confused at that level, what is this map? Well, this map, it's simply given by giving a structure, an action of E on V. You take an alpha and you take a little v. And well, you can say, listen, v, it's simply my E. So it has a very natural structure of E vector space. So why not multiplying by alpha, right? That's not good, because we said that this map should send to 0 the alphas that come from F. And if one does the computation, you see that the map that you get is, in fact, you multiply V by considering V as E vector space, but you divide by alpha bar. And then this makes perfect sense, and you have this factorization that you want. Okay? So even if this is confusing, at least we have understood what this map is, and the claim is that it lifts to a map to G spin such that it fits in this diagram. Okay? Okay, so now I'm just interested in the diagram. So the image of TE in G spin V, it's simply given by the quotient of TE via the modulo the kernel of the map. And the kernel of this map, so this map is injective, and the kernel of this map is identified with this kernel of this map. So I will simply write T, which is isomorphic to TE modulo the elements of TF. So this is, again, the restriction from F to Q of GM. The element of normal 1 is the image of TE in G. Okay? Very good. So I have a map in particular. I have just defined for you a subtorus of G, a subtorus of rank D plus 1. And the points are defined to be big CM points because this is the maximal rank tori that you can realize inside G. While, for example, the small CM points I was referring to are just two-dimensional tori mapping into G. Okay. Now, I want to cook up from such a map of algebraic groups, the inclusion of T into G, a map of Shimura varieties. Okay? I have the first ingredient, which is a map of algebraic groups. The second ingredient, it's given by defining a map of symmetric spaces. So the symmetric space for T, it's simply one single point. So I simply have to define for you what is its image in the symmetric space associated to G. Okay? And I just need to actually define to which negative oriented negative definite plane of VR I want to land into. So this is simply my E tensor QR. Okay? And inside here, I have what I denoted V sigma 0, which is simply E tensor F via sigma 0 of R. So this decomposes according to this decomposition where you vary the i's. You just have one copy, which is two-dimensional, where the quadratic form is negative definite thanks to my choice of lambda. And this is a negative definite plane. And you also have an orientation because I've chosen, I made a choice of the two embeddings of E into the complex numbers. Okay, so we have a map of tori. I have a very simple map of symmetric spaces. Now, to define Shimura varieties that I erased, and a map between them, I have to define compatible compact open subgroups. And now you see that this YL and Y0 will simply come from different choices of compact open subgroups in the adelic points of T. Choice 1 will be K0, which will be the product over primes K0P, and each K0P will simply be using the exact sequence that I smartly just erased. So remember, so maybe I can rewrite it. Note that I have a sequence GM T to TE modulo TF, okay? Because I've already mod out in defining T the norm 1 elements of F, okay? And then my K0P inside TAF will be simply an extension of ZP star and the most canonical compact open that you can have in both TE and TF. And then I define Y0 to be simply TQ modulo my symmetric space times TAF modulo K0. And then I want a second choice that allows me to compare the definition that I just gave with instead the Shimura variety that depended on a lattice and so on, is the definition of K0L, which is simply the intersection of K0 and KL in G of AF. So remember that I have a lattice L floating around and a compact open subgroup in GAF. This will be, again, a compact open contained in K0 by definition. And then I have my YL, which is simply GQ times Z0 times TAF modulo K0L plus a natural projection map to Y0. OK? So this is the zero-dimensional Shimura varieties that I can associate to my torus. One is canonical, fixed, doesn't depend on anything else. The other depends on a lattice that is floating around. OK? OK, so the reason that I chose this specific compact open subgroup is that you can find out, well, first of all, you can find out what's the reflex field or the field of definition of this Y0, and it's over spec E. But not only that, so via Shimura reciprocity laws, in these zero-dimensional Shimura varieties, you can also detect the ramification behavior of this map because the Galois action is given by class field theory using these compact open subgroups. And in fact, you can prove, so this is, so Y0 is a bunch of union of number field extensions of E. And as I said, you can see what the ramification behavior is using in terms of your compact open group. And in this case, it turns out that they are all unramified. So now I define, and this will be much simpler than in the higher dimensional case, I define Y0 and YL to be simply the normalizations. Well, this is finite, and this is even finite, et al. OK. Moreover, since I have a map from Z0 to D, from T to G, and the compact open that I've chosen for T maps to the compact open that I've chosen for defining ML, I also have a map to, this is not GQ, it's, sorry, TQ. I have a map to GQ modulo D times GAF modulo K0L, which is my MLC. And in fact, so here I abusively passed from a definition of a complex number, saying it can be defined over number fields. And in fact, yes, KL. Sorry, absolutely. Thanks. So the map over C defines a map from YL of schemes over spec Q from YL to ML, okay? And now, since my ML is the normalization, is defined by normalization, it's now difficult to prove that you can, in fact, complete this diagram. Generic diagram to a map on the level of models. Okay? So the only thing you have to make sure is that this does not go to the boundary, so to speak, but it's easy to verify. Okay, so we have our curly YL, our curly Y0, and the map to ML, and the metrized line bundle. Okay? So what I want to explain now is why this big CM cycle has anything to do with Colmez, right? Because this is, after all, this was our key ingredient to prove it. And I want to show, following the strategy that we already did for ML, that over Y0 we have extra structures. Remember, to define on ML the Kuga-Sataki abelian scheme and this V, Betty, Videram, and so on, we said, well, I just have to give you interesting natural representations, and then there is a machinery that does everything for you. Well, also in this case, let's look for interesting representations of T. Representations of T. Well, one we have because we said that we have a map from T to SOV. Okay. So that will give us, for us, certain V Betty. Let me write 0 because I'm really doing it on my small dimensional Shimura variety. I have my Videram 0, which will have its field 1. There will be no connection in this case because it's 0-dimensional. And all these will live over the complex point of C. There's another one which has to do with the total reflex algebra. So let me try to do the algebra right. Okay, so let's start with my V tensor QC. So this is simply E tensor QC. And now I can use the fact that this is a field to give a complete splitting according to canonical idempotence, right? So these are the canonical idempotents, so that this is really a splitting as algebras. Which means in particular that I can, since I have a basis for this space, I can describe the full Clifford algebra and the Kevin Clifford algebra in terms of tensors of those elements. Okay? So in particular, I define for every, let me write a generic rho in home EC. Let me define delta rho to be 1 rho lambda of E rho bar in C plus V C. is my V. And for every CM type, let me write delta phi to be the product of a whole row in phi of delta rho. These again are elements in the even Clifford algebra because they are the product of even tensors. And now lemma, if you take the sum over all CM types of E of C times delta phi inside C plus of BC, this is a C sub algebra having delta phi as a standard canonical idempotence. Meaning that each of them is an idempotent element. The product of two different ones are 0, and the sum is 1 in the even Clifford algebra. Okay? Not only that, for every element, for every G in the Galois group of, well, Q bar over Q, so these idempotents and so on, they relieve inside algebra over Q bar, you have that if you act, so my delta phi really live in C plus V tensor Q bar, so you can sort of act via the Galois group. This is invariance, and the Galois group acts on Q bar. This is simply given by the action on the CM types. Okay? So that it means in particular that my subalgebra that I've split completely is a concrete incarnation of the mysterious looking total reflex algebra. Right? Because I told you that, so this is the unique état Q algebra with the property that as a Galois set, it is isomorphic to CME. And how can you see the Galois set action? You take your algebra, you pass to an algebraic closure that splits completely, and you look how the Galois group acts on the standard idempotence that you get. Since they are the same as the algebra that I have described, I get an incarnation inside the even Clifford algebra of the total reflex algebra. Okay? Conclusion. One, we have embedded E sharp inside C plus V as a subalgebra. 2, the map from T to G spin V factors via the torus associated to the total reflex algebra. Why? maybe I can simply rewrite the map that I very confusingly wrote before. Well, maybe, so let me maybe write something different. Let me write so you can realize the image inside T sharp. Let me instead write for you the action of E on E sharp is given. So let me just write what is the automorphism group of E sharp that you get from this map. So I'm not simply describing the factorization on the notes I do. Well, so you have a map from E star from E sharp to E sharp, and the map is given as follows. If you take an element little x in E sharp, and I simply will tell you where it sends this idempotent, even if it's defined over C. And it's defined simply in the only way that you can think of using your CM type. It's simply the product over all rho in phi of rho of x times delta phi. So you can prove that this map induces a map from that torus to the torus T sharp. In fact, the map from TE to T sharp that is defined in this way is called the total reflex norm, if one is interested in terminology. And one can prove that this is exactly the composite with the inclusion inside G spin is the map that I defined originally. Okay? Oh, I had a lot of time. I went too fast. Okay, so that is to say that we have another interesting now representation of T. Right? Because I have a map of tori, particularly it acts as automorphism of Q vector space on the vector space V sharp, which I simply denote to be E sharp. So let me erase this. So I want to leave example 1 on the blackboard. And now I have example 2. I have a map from T to GL of V sharp. So you should think of this as the analog that we saw yesterday of the fact that G spin admits a map to SOV. That gives a first interesting variation of our structure and so on and so on. And then it admits also a map to C of V, which allowed us to define Kuga-Satake abelian scheme, right? So example 1, example 2. And exactly in the example that we saw yesterday, we saw that you can embed as representation of the group G spin V inside the endomorphism of the Clifford algebra. And in this case, the same happens because we have a homomorphism of T representations that go from V to the endomorphism of V sharp. So you get the exact complete analog of what we saw in the G-spin case. Let's see, how do we get it? So this I can write as V sharp tensor V sharp dual. Here I have to let me remember that this is E, that this is E sharp tensor Q E sharp dual. And well, to describe this map, then I simply have to tell you where some E rho what do you want to say? E rho goes to, right? Let me see if I remember. Where did I write it? Yes, okay. So let's see. So I want a map of T representations. Here, T or TE, if you want, acts by sending an element alpha of E. So, so an element alpha of E acts on E rho by rho alpha divided by rho alpha. Okay. Here instead, the action on the delta phi is described in this way. Okay. So the action here is simply given by taking the sum over all CM types that contain rho. So on those, your E will act via rho and other stuff, okay? To get an action by rho alpha divided by rho bar alpha, I want to kill the other stuff and divide by rho bar of x. So I simply take here delta of phi, okay? And then here I simply take delta phi smashed with rho, where this phi smashed with rho simply means that I take out my rho and I add rho bar, and I should add a dual. Okay? Has interesting consequences that I want to describe. So now using, so I told you yesterday that these representations will give us variation of Q-odd structures and amorphisms. And if you choose lattices, which are preserved by K0, for example, you get even Z variation of odd structures, okay? And here I have good choices. So I have the lattice OE inside E, which is my V. And this is really preserved periodically by K0, by our choice, okay? I also have my O E sharp inside E sharp, which gives my V sharp. I get on Y0C exactly as we saw yesterday. So one can prove that this V sharp is a variation of odd structure of type -1, 0, 0, -1. Which is an abelian scheme, abelian variety with full CM by OE sharp. And so this will be the de Rham cohomology. And sorry, it's V sharp. V sharp, right. So this is the, so the de Rham cohomology will be just the sum of the complex multiples of delta phi. And the part -1, 0 will be the sum of the delta phi that contains our original embedding sigma 0 of E into C. And the orthogonal complement, the other part, the quotient part, the 0 -1 part, is instead the sum over the delta phi that contain sigma 0 bar. So the CM type phi sharp. And then I get an embedding of some v Betty 0 inside the endomorphism of H1 A sharp. And also a map from the Ram realization inside the end of H1 the Ram of my, say, A sharp. So far over the complex numbers. Okay? Okay, what can we say more? So first of all, one can prove that this action of E via alpha alpha bar, from that action, you can recover the full OE action. So this decomposes over I0 to D as V0 de Ram sigma I plus V0 de Ram sigma I bar. Remember, so these are 2D dimensional C vector space. And here I'm just decomposing according to the eigenspaces for the action of OE or E in this case, since we have the complex numbers. And then my omega 0, which is my field 1 of V0 de Ram, it's simply the part where my OE acts via my preferred embedding of E into C. Okay? But this maps to field 1 of H1 the Ram of A sharp. H end. What is field 1 of end of H1 the Ram? Well, let's see. So my H1 the Ram, so I'm working with homology, so I have to dualize the usual Hodge exact sequence. Maps, I get a map from to the dual of the differentials. And here I have my H1 A sharp O A sharp. I rewrite it. I write my, sorry, H1 dual. Right, so I have a filtered vector space, and that induces a filtration on the endomorphism. What is field 1? So field 1 is exactly those endomorphisms that, so field 0 are simply the endomorphisms that preserve the filtration, and field 1 is the morphism that sends one grö, the grö to fill. And maybe instead of writing H1 A sharp, let me write H0 of the dual abelian scheme. Okay, so in particular, I get a map from omega 0 by taking, so that's a line bundle. Locally, I get a map from a vector bundle to a vector bundle. I can take its determinant. So I get a map to the determinant of H0 A sharp, omega 1 A sharp, and this dual disappears, right? Times the determinant of H0 A sharp omega 1 A sharp dual. But this is simply the Hodge bundle of A sharp tensor, the Hodge bundle of the dual. Okay, so I did it simply over the complex numbers. But now by my integral theory, I can extend A sharp over the whole integral model. I can extend also my V0 over my integral model. And that I can do because I'm in dimension 0. So I can apply directly Kissin's theory to have models, p-adic models of my integral structures. And I get all this structure, all this passes to, or extends to y0. So this is a metric also. At infinity, defined by simply minus z bar, as we saw. These two have a Falting's metric. And then I have a comparison between line bundles with metric, line bundles with metric. And I can sort of see where this line bundle differ from this line bundle, how this metric differ from this metric. They will, because here, no, not they will. Yes, they will. But one can sort of explicitly compute what happens. And that's the result I want to finish with. So theorem. So comparison of degrees. So this map here, so we get that I think I forgot here, right? So if I take the determinant, I have to take a power, right? Sorry about that. So I get a map from here to here, passing to the determinant, I get powers of the omega 0. Sorry about that. And we get that the final result, that 1 over 2d of the Falting's height of E sharp phi sharp, this is measured by this, because also the dual will have an action of OE sharp, and you know by Falting's that an abelian variety and each dual have the same height. Okay? So this will be computed by the right-hand side. This is equal to what? It's equal to the arithmetic degree of my omega 0 hat. Well, here remember that my big CM cycle will consist of many points, right? And here, in a sense, I'm interested in the height of simply one of the representatives. So I have to remember to divide by the number of points that I have. And then there is a 4. And then there are two contributions. There is 1/4 of the discriminant of the total real field that comes from the fact that this map is not an isomorphism exactly at the primes that ramify in OF. And that's an exercise in algebra, quite difficult actually. So because you see, I defined for you an action of E on E sharp. Now you can take this to an action of OE on OE sharp, right? And now you want to see when you pass to, when you sort of, if you tensor with the ring of integers of some number field where all the embeddings exist, so that you can talk about field 1, you want to see how that fits inside the map from OE sharp tensor with this ring of integers to itself, okay? Whether it's surjective or not. So it's really, in a sense, like comparing, if you want, if you have the ring of integers of a number field, Galois, OE tensor OE, with the normalization of OE tensor OE. Yeah, and you see that the two differ exactly at the primes which ramify. So it's this kind of phenomena that you have to check. And then there is another contribution, but I lost the, okay, which comes from the comparison of metrics and from the fact that you normalize the Faltings metric by dividing by log 2 pi. Okay, so that's good. So via our Shimura, zero-dimensional Shimura variety, with all the extra data that maybe I've explained it too quickly and too badly, but at least they look very much analogous to what we did yesterday for the group G-spin, okay? So you have two representations, a comparison between them, and you want sort of to get extra data. From that, we managed to compute the Faltings height that we want, okay? So at least we have done the major reduction step, and what remains to be done tomorrow is to compute the degree of this Hodge bundle. And what we will do is to pull it back to YL and compare it to the metrized line bundle on ML. And that comparison we can make only up to finitely many bad primes that I will discuss how to deal with. I'll stop here. Thanks.